Okay, so essentially we want the sum of the k1 through kn to be 1 mod 5. And then we want the sum of the reciprocals to equal 1. Oh, and okay, so there's n of these, and then actually the sum depends on n, so there's a stronger condition. So what does that mean? It means on average they're around. Okay, so these k average is roughly 5. It's a bit less than 5. Okay, so we have what? Okay, so I want this to be true. What is the harmonic mean of the numbers? That's going to be n over the sum of these, which is just equal to n. And by HMAM, this is at most the average of the k numbers. Yes, HMAM. And this is equal to 5 minus 4 over n. So we immediately have this condition. And we can see what satisfies this. It's going to be like something that looks like that. Okay, so we can rearrange this in quadratic. We have n squared equals less than or equal to 5n minus 4, and then n squared minus 5n plus 4 is less than or equal to 0. And this occurs precise, so we can factor this n minus 4, n minus 1. Okay, so we've essentially narrowed down n already into. So basically, n is between 1 and 4. And if n is 1 or it is 4, so if n equals 1 or n equals 4, then this expression precisely is 0, which means that these two expressions are equal. This forces these to be equal. So that means that all the numbers are equal. So in this case, what we have k1, well, that's kind of trivial. We have k1 is equal to 1. Otherwise, for n equals 4, we have k1 through k4 all equal. And the sum is equal to 4 times 16. So that means that k1 through k4. So we already have two solutions. If n equals 1, then k1 has to be equal to 1. If n equals 4, then the sum of the ki have to be 16. So that means the k1, so every ki is equal to 4. Yes. So those are the only solutions for n equals 1 and n equals 4. Yeah, okay. And then, okay, confirm this actually is a solution. Yeah, that's good. That's good. Okay. So if n equals 2, so we have two cases to consider. N equals 2. So k1 plus k2 is equal to 2, no, 6. Yeah, okay. And then, okay, we can just check those manually. And likewise, we have k1 plus k2 plus k3. This has to be equal to what? 11. Yes, 11. Okay. And then we want the sum on 1 of k1 plus 1 of k2 is equal to 1. Well, how can we do that? Well, you just kind of guess, don't you? And see what works here. You can have 1 over, so no, 1 over 1 doesn't work. So you have 1 over 2 and 1/2, 1/4, 1/3, 1/3. They're positive integers, so there's only a finite number of. This doesn't work. This doesn't work. Okay, so this is not possible. Okay, that leaves n equals 3. Sum up to 11. The reciprocals sum to 1. Okay. Now we can write the sum 1 on k, 1 on ki. This is just cyclic sum of k1, k2 over the product of ki, and this has to be equal to 1, so that means that this is equal to that. Yes. Does that help? Not really, but still a finite number of possibilities to check, I guess. Do I want to check them all? Is there a better way than checking them all? I could, because it's not that many, I guess. And you want 1 on k1 to be 1. Okay, so first of all, let's see, this is, okay, this, if the sum is constant, so I know that this is minimized, yeah, because HM is maximized when the equals. So this is maximized, therefore this is minimized, so some of this is minimized when they're all equal, and the equal list they can be is like 4, 4, 3. When I do that, I get 1/2 plus 1/3. That's 5/6. Okay, so the minimum is less than 1. That's what we expect. Okay, let's condition on, for example, K1. So if K1 is 1, it doesn't work. Okay, if K2 is 2, okay, actually, we can break this down. So we have K2 plus K3 is equal to 11 minus K1. So we're treating K1 as variable now, and then we have, so K2 plus K, 1 on K2 plus 1 on K3 is equal to 1 minus 1 on K1. Okay, pretty sure we can come up with a way to solve this uniquely. Yeah, okay, so this is just the sum K2 plus K3 over K2 K3, and this is equal to 11 minus K1, which means that K2 K3 is equal to 11 minus K1 on 1 minus 1 over K1. So K1 minus 1, and then multiply this by K1. Okay, we get this, and this has to be an integer. So I think we can check all the K and show that we need to make sure that K1 minus 1 divides 11 minus K1 times K1 for all K1 from 1 to 11. Or actually, from 2 to, okay, these, none of these can be 1, so these two are both at least 2, so that makes this at most 7. Okay, I guess it's time to just list them all out. 1, 2, 3, 4, 5, 6, 2, this is 9 times 2, 8 times 3, 7 times 4, 6 times 5, 5 times 6, and 4 times 7. This doesn't work. This is fine. This doesn't work. This doesn't work. This is fine. This is fine. Okay, that means that K is equal to either 2, 3, or 6. Okay, let's check each of those possibilities separately. Oh, in that case, we can actually compute what K2, K3 is. So in this case, K2, K3. So it's just the product of these divided by that. Okay, so this is 18. In this case, it's going to be, what, 12? And in this case, it's just going to be 6. And I know the sum, K2 plus K3, is just going to be 11 minus K1. So this is K1 minus 1, this is K1. So this is going to be 9, this is going to be 8, and this is going to be 5. Yes. Work out, that work out. Okay, now we just need to figure out whether these have integer solutions or not. Yeah, this says, and if it does have an integer solution, I think the solution will be unique, yes? Yeah, well, because you can rearrange it to quadratic that has most 2 solutions, and I know that 2 of the solutions just come from symmetry. Yeah, so this is going to be the unique solution. So you have a solution here where you have n equals 3, K1 is equal to, oh, this is up to symmetry, of course. K1 is equal to 2, K2 is equal to, so you have 2, 3, 6. Okay, that works. What's going on here? H12, so you can have 6 and 2. That's just isomorphic to the solution. And then 6, you have 5, 6. Okay, so this is the only solution up to symmetry. And I think we're done. So here's one solution, here's the second solution, and here's 6 more solutions up to isomorphism.